First of all, thanks to everyone for staying. This is officially the last talk, so I appreciate seeing so many people here. And yeah, my talk today is building custom tokenizers, AI for underrepresented languages. And basically, this is a keynote for the paper that we'll be releasing sometime end of this month in collaboration with a bunch of researchers, including Arab Center for Research and Policy Studies and the Doha Institute for International Studies. So a little bit about me and why I'm doing this. I'm an AI engineer, serial entrepreneur, ran venture studio, built a bunch of startups, ran nonprofits, and continue to do interesting tech stuff. But actually, when I was a kid, I wanted to be a doctor. But being born in a post-Soviet country, in a dynasty of doctors, I was specifically instructed not to be a doctor because you won't have any money. So that's how I became engineer. But you can't escape the fate, and I kind of joked that I became AI doctor. And hence, the alternative title for my talk is why neurosurgery of the models is all you need to build the AI for underrepresented languages. So before I dive in, a lot of people, when they hear me talking about AI for underrepresented languages, they kind of make a strong claim that, hey, isn't Claude and GPT-4o good enough? It's pretty great in other languages. And it's a very strong claim because all of these models are still English-centric models. And the phenomenon that I want to explain here is what is called the curse of multilinguality. And basically, it's the more training data you feed into the model that is other than English, the more the model gets confused in terms of the actual modeling of the language. And you get these interesting side effects as a result, including code switching. Sometimes you ask something in Ukrainian, it answers you in Russian or in English. Sometimes it starts writing the word, the part of the word is in Arabic, the other part is in English. Or it replaces the words with Japanese or Chinese characters of all sorts. And this is the phenomenon that is basically observed across the board in all of the models that claim to be, multilingual. The other aspect is that all of these models are actually amazingly good at inventing non-existing words. And I mean the words that you kind of read, and you can read the word, but it definitely doesn't exist. And the other side effect is the fact that those models hallucinate even more because they lack that local context, and that's why there's way less probability of generating truthful answer. And of course, as I mentioned before, English-centric bias is a thing. So everything is normalized to English-centric concepts and also to the skewed averagization, of the internet, which is not a good thing on many dimensions. On the cultural identity dimension, on the economical dimension, on a defense, military, those kinds of use cases, you can't really have those things. And that's why I'm a true believer that you have to build specific models for specific languages, and it matters. So the other aspect is actually the hidden cost, because it's not just about the cleanliness of the language, but also viability, the economical viability of using these models. So when you take the same sentence in Ukrainian and in English, it's actually 3 times more tokens, which means it's 3 times more expensive. It's almost like a taxation, like a penalty for using other language. And obviously that renders those models, basically, they're not viable for those markets because those markets already don't have any money. So that's even more, unviable. So the issue here is the actual inefficient tokenization. What you see here in these colored blocks, those are tokens. So the tokenizer is basically the root of all of this. That's why, we have a problem. The patient has clearly the monolingual syndrome, and we can't easily fix that because, we can't really grow a new patient. It will take many years for us, GPU poor parents, so to say. And obviously, we don't have money to do that. So as a result, we have to invent creative solutions to fix for that. And the creative solution that we are suggesting is a neurosurgery and the rehabilitation. So when you do the neurosurgery, as I mentioned, the tokenization is one of the most important parts. And that's where you start. Why? Because tokenizers, as we probably heard in the previous talk, are very important, both for embeddings and the actual parametric knowledge. Because tokenizer breaks down the language into the actual tokens, words, subwords, characters. And it converts that text into machine-readable form, which also is essential for the model's understanding. And here's some fun and sad facts. Mistral has less Armenian tokens than an actual alphabet. Mistral has less Georgian tokens than an actual alphabet, but Georgians got one more token. So I guess they're statistically speaking better represented. Aya, Cohere's model, that is the most multilingual model, and I really respect their efforts in building multilinguality, but apparently it has 8 Armenian tokens, which is less than basically tokens to represent arrow symbols. And statistically speaking, I guess the arrows are more important than Armenian language. We know that's not true, so that's why that's not really acceptable state of the industry. Then you take Gemma model, which has one of the biggest tokenizers, 250,000, and it only has 244 and 99 tokens for Armenian and Georgian. So that's why this part is important. It's sad and it's not acceptable. So when it comes to preparing for this neurosurgery, our goal is really to enhance the X language capabilities without damaging existing English skills. Because we're relying on the model, we're not building the model from scratch, so we can't really damage those. And our approach is bilingual vocabulary extension. And patients are Gemma and Mistral, and those, we've done the surgical procedure, basically preserving vital English pathways, identifying and strengthening existing neural connections, and implanting the new language capabilities. So here on this table, you see what we've done for Arabic, Georgian, and Ukrainian. You can see that previously, for Arabic, Mistral had only 83 tokens, and we bumped it up to 2,800. Georgian, 29 tokens, bumped to 5,000. Ukrainian, it had 1,000 tokens, we bumped to 4,000. And the reason why Ukrainian has 1,000 here is not because, Silicon Valley likes Ukraine more. It's because it's actually very hard to distinguish which tokens are Ukrainian, because a bunch of languages are using Cyrillic script. So you can't really say whether those tokens are a part of the Serbian, language, or Belarusian language, or Ukrainian. So it also doesn't help with the code switching, as you can imagine, because models actually code switch into those languages way more. So after you've done the vocabulary extension, the next part is restoring memories. The previous speaker spoke about embeddings, and someone asked about the initialization of embeddings. And we are probably I'm happy to claim that we're the only crazy ones that spent a lot of compute to test different things. And we tested residual, mean, we invented our own approach called nachos, and we tested probably the most interesting, popular one, focus. And I kind of in terms of metaphorical approach, residual initialization is basically a bed rest. You don't do anything, and the model just recovers with the minimal interference. Mean is basically physical therapy where exercises new language capabilities through average movements derived from existing skills. Nachos, the one that we invented, it kind of breaks down the new language skills into smaller, familiar components that the model already knows. And focus is like cognitive behavioral therapy that uses precise techniques and actually external guidance to strengthen those specific language connections. So after you initialize the embeddings and restore the memories, the model still haven't seen those new tokens. So you still have to adjust the weights and do the actual continued per-training. So that is rehabilitation. You basically carefully exercise new language capabilities, You monitor for signs of catastrophic forgetting, because you can't allow for that when you're relying on those existing models. And you gradually expose the model to more data and more tasks. As a result, this is one of the experiments that we've done, where you can see how the model starts picking up those new tokens. So here you can see it actually starts using the old Ukrainian tokens here, but then gradually, that value decreases, and the new Ukrainian token, the orange line, starts going up. Simultaneously, the English tokens are decreasing. And what I wrote here, that Mistral stops being a cheating student that speaks English and starts to speak proper Ukrainian. And surprisingly, it doesn't take as much time to actually see proper language being generated once you do this whole exercise. So we've done the same for Georgian. Because Georgian was so underrepresented, you can see a much higher value for the new Georgian tokens being picked up right here. And obviously, there wasn't that many in the first place. Almost similar situation to Arabic, because it was so underrepresented. So you can see the new tokens being picked up right here. So after you've done all of that, the question is, how do you measure all of these things? So there are two metrics that are considered intrinsic evaluations of tokenizers: fertility and parity. So those kind of exist, and it's super easy, well, not super easy, but relatively easy to do those tests. But how do you evaluate the actual inference in regards to that curse of multilinguality? Surprisingly, there were not that many metrics out there for this. So we had to invent those metrics for code switching and for known existing words. So tokenizer fertility and parity, for those that are not familiar with the terms, fertility is the average number of tokens required to represent a word or document. Parity is having similar tokenized length for the same sentence in different languages. So what we've done, we've actually achieved almost English fertility and parity, and tested it on two data sets, Paracroll and Makoku. The reason why you see the deviations here is because those parallel corpuses are actually machine translated, so we have to account to some deviations there. The non-existing metric was basically our first attempt to eliminate or test for the elimination of those made-up words. So it's basically a simple heuristic where if that word doesn't exist in a corpora, probably the biggest corpora that you want to test on, most probably that word is made up. So here you can see the actual prompts in Ukrainian and then the completion results. And most of this stuff doesn't even make any sense. And some of the words, if you read them, you may wonder, is it me that I don't know that word? Or does it really, is it a made up word? And obviously you can put it in Google, and guess what? There's zero mentions of this word, which is quite fascinating to me as the ability of LLMs to generate this, quite interesting side effect. So the next metric is the code switching, which is a phenomenon when a speaker uses two or more different languages in conversation. Obviously, it's familiar to Armenians because of Russian, and the same for Ukrainians, same for Georgians, because sometimes we actually naturally code switch or use words from other language. But in the process where LLM generates a text, it's not really linguistically correct when it comes to symbols, words usage from other languages. So here, the actual completion is Ukrainian. And then you can see how the model starts generating Arabic script. And that's a thing for multilingual models. Or here, you see the completion in Ukrainian, and then boom, Russian word. So it's quite an interesting problem to solve. And we had to do various rule-based metrics inside this code switching metric for each language to account for linguistic differences. Because the only metric in this space that existed before was the recent one developed by Cohere, and they called it language confusion metric. And it was designed for languages using non-Latin scripts and is applicable for Ukrainian, Georgian, Arabic, Armenian. But this metric fails to include language-specific rules when it comes to code switching. It provides a good understanding of which language response is leaning towards to, but ignores those language-specific rules. For example, here you see Ukrainian prompt that generates a list of computer games. And in reality, this is not a code switch because we don't expect people to transliterate these things into Ukrainian. But for the language confusion metric, it detects it as the language confusion, but it's not. So we account for that, and the code switching metric works correctly. So let's talk about actual results. Here I present the case of Mistral and the Arabic tokenizer that we've done. The results is basically an inference on 1,000 completion prompts that we've generated based on the top Wikipedia articles in a given language. So what you see here is that we originally had, with the default Mistral, 54,000 of non-existing words in the produced results. And it goes down to just 2,000 as a result of replacing Tokenizer. You can also perceive it through the existing words ratio. So basically, only 24% of the words in the results existed. So it's basically increased to 96%. And the switching ratio dropped from 34% to 10%. The language confusion, is a much simpler metric. So you see here from 35 to 1. But it's not just about the cleanliness of language, as I mentioned before. It's also about the economical viability of those models. And that's why we have to actually research the efficiency and the performance of these models. So because the LLMs are basically bounded by hardware constraints, it will always generate, for example, 80 tokens per second on on A100. But in reality, when you inspect the characters per second, you see the difference. The default Mistral is 105 characters per second. The one with our Arabic tokenizer is twice more, 209. Which means in the actual downstream applications, like generating articles, on average, it takes back and forth to generate those articles. So for example, it may take 31,000 tokens per post. And if you do that with the LLM with the Arabic tokenizer that is specialized for that, it's twice less. Which means it basically takes twice more time to generate that for 1,000 samples. So instead of 4, almost 5 days, you get 2 days. And these first kind of like metrics, they don't really make sense to business people, as I joke. But these ones, especially when the dollar signs appear, this is a big one because you get basically a penalty for using other language. If you're a business or a government trying to implement LLMs, these are super, super important things that you're going to optimize for. And it's impossible to do that without diving into tokenizers. So in terms of future work, obviously this first research paper is designed to bring awareness to the issue and also showcase different initialization techniques, different approaches. We want to build more efficient tokenizers that are based on the actual individual language nuances. So morphology and different approaches to that, not just frequency-based. We truly believe that will lead to a much better performance in downstream applications, which is why we want to research the downstream applications and impact of tokenizers. There's already research that researches some of it, but there's very little specialized to downstream tasks. And we want to improve language-specific code switching detection with the actual model, because crafting those rules, it's kind of like insanity when you try to account for all the rules per language. So with that, I'll start wrapping it up. Obviously, my name is Artur Kilian. You can read my article about why AI is English-centric and why it's a big problem. So hit me up, follow me on LinkedIn. The last point before I open up to the questions you may, sit here and wonder, you did, Arabic, Ukrainian, Georgian, but Arturjan, where's Armenian? Like, what happened? And the thing is that I wasn't born in Armenia. I was born in Ukraine, and I'm quarter Armenian. I look 100%, but I'm only a quarter. But I don't speak Armenian. I would love to, and I truly believe that Armenia needs this. The population, the culture, and we should do this. But we can't do this, ourselves. That's why actually I'm here. Not just to reconnect with my roots, but also find people that are passionate about the topic and help, collaborate on this project. Because essentially it's impossible to do without local people, without people that are passionate about this. If someone thinks that, a group of people in Silicon Valley will build a better Armenian LLM, that's not going to happen. Because there's so many nuanced things that you have to account for that you need local engagement. So with that, thank you so much. Open for questions.
Thank you for great presentation. I have one question. For example, if I have a GPT-2 model, for example, and I want to train it for Armenian language, fine-tune it for Armenian language, I need to train the tokenizer as well, GPT-2 tokenizer. So when if I train the GPT-2 tokenizer, do I need to train the model after each time training the tokenizer, retrain the model?
So basically, and that's why I took the analogy of neurosurgery, because we're kind of like taking the existing thing, taking things out of it, training the tokenizer, then injecting it back, and then trying to fix things so that model is not stupid, right? And GPT-2, to be honest, is pretty stupid, compared to the existing like 7 billion models. So what you have to do, you have to train tokenizer once, inject it in there, but if you're modifying anything else in the model, you still have to, basically fix the weights and the embeddings in regards to those tokens, because the model never saw those tokens. It's like, it just doesn't know what it is.
So every time, for example, when I get more data, I need to train the tokenizer and the model also, yeah? Or just the model?
Just the model, assuming that you picked out the most representative corpus of text to build a tokenizer. Because if you train it on a small corpus, you'll get bad tokenizer, basically. Yeah. And I mean, this is a challenge in terms of the availability of data sets for low resource languages. But I mean, as long as you have millions of speakers, you have pretty much some data that is enough to build a custom tokenizer. It's way worse for, for example, Okinawa language, the island nation where there's under, I don't know, like 500,000 people, and there's no digitization of it. So, our languages are not in that bad condition. We can still do it.
Thank you.
Thanks for the talk. I wanted to ask something a bit maybe philosophical in a sense. So, for the first part of the question would be, what do you think about like a scenario if I somehow manage to mix up a set of tokenizers to create like a generalistic tokenizer of all the languages in the world? And the second part of the question would be, do you think it is possible, given some linguistic properties of languages, to learn a direct translation, not from language to language, but maybe from morphology syntactic to the syntactic of the other language?
So the first one is, are you talking about merging of tokenizers?
Merging, retraining together, whatever type of a technique you fancy for.
So as of recent, MergeKit added the capability of merging tokenizers. We tested it. It doesn't work. I don't know, like considering the levels of abstractions that we keep seeing in all of these frameworks, it's hard to say whether, we have done it wrong or they have done it wrong, but so far I haven't seen it working. In terms of building the tokenizer that represents all of the languages equally, I think we won't see that, because you either have to build like million token, vocabulary tokenizer, which immediately renders the actual downstream, training performance and all of these things. So I don't think that will happen. But transferring from one language to another one is interesting, because the reason why we want to do the morpheme-based tokenizers is because each language has unique approaches to how the words are built and all of these things. And we believe that moving from language to language, we can actually learn some similarities, especially by family groups. So I'm a big believer in that direction.
Thanks a lot.
Thank you very much. Very nice talk. I have two questions. The first one is about catastrophic forgetting. You mentioned that, but you did not show some metrics on that. Will you please share how you measure this forgetting and how you make sure that that will happen? And the second question, maybe it's more complicated. You specified that today language models are AI assistants, or they are trained with a relationship and all this fancy stuff with this aligned data. And you have to have this aligned data for new languages. So what is your opinion on that? Maybe we have some chances to transfer those learnings from English to some other languages, or we have to collect some data set, or maybe we have to do machine translation for the data set. Interesting to hear just your opinion.
I'm going to start with that because that's my favorite topic of alignment. Silicon Valley in general thinks that it's possible to find the ultimate alignment that works for everyone, right? That the model will be, good to everyone. That's not how the world works. The history, the perspectives, all of these things are different for different regions, different cultures, different social norms and values in all of these things. So I don't see the possibility of transferring that. It actually has to be built in by Armenian community, because it's people of Armenia should say whether the model is good in Armenia. It's not the Silicon Valley researchers that claim, oh, it doesn't say this and that, it's good enough for Armenians. No, it should respect the history, the perspectives, and all of these things that are relevant. I'm from Ukraine. There's so many things that models, misrepresent, and especially with this kind of like moral relativity, they just fail to account for the fact that we as Ukrainians don't really want that moral relativity. Like, we need exactly, what the model should say for us and our usage, because we are the ones that will be using it. So that's the first one. The second one, what was it? Forgetting. So the easiest way to do this is MMLU, which is a kind of like a weird benchmark, but it's good enough to test whether the model forgot all of these things from before. And the more it drops, the more it basically forgets. There's a bunch of benchmarks that you can use, but we just use MMLU as the simplest one.
And it works. It doesn't drop, or it drops like.
It does drop, and that's the part that we want to focus on in another research paper to do the actual, if I ask someone, does the Armenian version of MMLU exist? Do you know?
No.
It doesn't. And the first version that will probably exist is just machine translated version of the English one, which doesn't make any sense. Some of the questions will be weird and all of it. But when you test for forgetfulness, it's important to understand that there's a balance, right? The shaky balance. You want the model to learn new stuff, like the stuff that it never seen from the history and all of these cultural things that were never absorbed in the common crawl. And you want to preserve the basic knowledge of the world, all of these things that exist in the English model. So it's actually a very challenging research problem, how to avoid that forgetfulness.
Thank you very much.
Thank you for your speech. For estimation, you are using non-existing words, but it's depend on prompt. How you choose what kind of prompt it's clearly depend on prompt.
So we published first paper, I think April or so, about fine-tuning models, Gemma and Mistral for Ukrainian. And we found out that there was actually no instruction data set for Ukrainian. So we created that out of the top 100 Wikipedia pages. And we followed the same pattern here. We basically took the Georgian Wikipedia, Ukrainian Wikipedia, Arabic Wikipedia, generated the instruction data set, and then took a part of it to produce stripped completions. So basically those are things that models should be actually good at completing because it's public data and it's most popular stuff in that language. So those are completions that we tested it on.
My answer is you have million prompts, but you are using 1,000 and estimate how you choose 1,000 prompts from this space process.
Yeah, we take Wikipedia articles and then we generate the instructions based on those articles.
Okay.
And then we take we basically took the question answer fact, so the triplet, and then we took the fact, which is basically descriptive factuality, and stripped it to like 2-3 words. So basically letting the model to autocomplete, because we're testing base models here. This is pre-instruction training.
Second question. I have a friend, he writes prompts in 2 languages in 1 sentence. And he said that is the helpful for training, fine-tuning models. Is it?
Probably. I don't know. We need to test it.
It's another type of question for Eric.
Yeah.
Okay.
So Armenian language, you have a few million speakers. Let's say Portuguese language, hundreds of millions of speakers. And not only Portuguese, like ChatGPT, you take internet in Portuguese, it doesn't have a lot of information. If you're a doctor who speaks Portuguese, you want to look up something, you better have a friend, doctor, who speaks English, who can look it up, read it, and translate it to you, tell it to you in Portuguese. Of course, do you know how do you solve this for Portuguese, like this forgetfulness problem? Because if you solve it, if you solve it for Armenian, and you can solve it for the last languages. So I don't know. It's just like have you thought? I'm sure you thought about it. Like, what are your thoughts on that?
Yeah, so I'll start from the fact why what I'm doing, was Open Babylon is an actual commercial thing. Because I tried to do this as a nonprofit, as a social impact thing, and I quickly failed because even though we don't need hundreds, thousands of GPUs, we still need GPUs, right? And getting compute nowadays is super hard. So my idea is that we can do it for languages like Portuguese, Arabic and others, where there's much more data and basically there's more funding, because those are actually markets where there can be some revenue generated. So we will do this for Portuguese. And then, obviously the languages like Armenian, Georgian, Ukrainian, Uzbek, all the others, there's very little incentive for anyone to do this. So unless we find the commercial, markets and build the infrastructure to be able to do this for other languages, or no one will do this. That's my current assessment of this. So we have to do this for Portuguese, for Arabic, for Indonesian, and we'll get the side benefit of having infrastructure to do it for the others.
Yeah, so you feel it will if you solve it for one, it will just scale for everything, right? Because you don't have to.
The infrastructure will scale, and the learnings of doing that. For Portuguese, you get different challenges, because even Spanish is pretty bad in models. I was surprised, but there's a bunch of research papers on that, and it's still because the models are English-centric. But it's possible for Portuguese, and yeah.
I have a few questions. First is a very small and technical one. One slide is code, and you use the term code switching. Do you mean by that language code? I suppose.
I mean the actual language. The code switching is exactly this. When the completion falls in one language and then it switches to another one. So it starts producing the Arabic script.
Rather than speaking about source code, this is a language code, but maybe not so formal.
It's actually a linguistic phenomenon. We didn't invent the name for it.
Let's recap the overall procedure that you, as an AI surgeon, suggest. So you enhance the tokens with new tokens. After that, you run the learning that transformer machine GPT engine on the text and do some representation practices that will really help it. Am I right in this recap?
Yeah, pretty much. We build custom tokenizer, we inject it back into the model, we connect the embeddings, initialize the embeddings, and then we do the training so that model picks up the tokens and learns new knowledge that also didn't exist there.
Okay, great. So my question is, how do you get these new tokens that you inject into the language? How do you generate them at the first place?
Yeah, so as I mentioned, it's still frequency based. And this is the scope of the first paper. We kind of already done a lot, so we pushed that into the second paper that we'll be doing next. But that will be the one was the linguistic approach to tokenizers, which I truly believe will render much better performance. Because the frequency-based approach is pretty much the Silicon Valley mindset. Let's just throw a bunch of compute, a bunch of data, and somehow it will work. And it kind of works. That's how all of these beautiful models were created, but to some extent and in the context.
Can you say what algorithm do you use for that?
It's BPE. So we use the sentence piece models and BPE. Yeah, it's the industry standard.
Okay, let's thank Artur once again, and if you have further questions. Yeah, you can talk to him later or
Awesome.
after.